Hi, this is Aiden. We're going to do some sample problems today. We're going to be focusing on angular momentum. Very fun, the big L. We're going to be doing two sample problems actually. We're going to be focusing on the ladder operators at the top step and the bottom step of the angular momentum ladder. We're going to be talking about quantum numbers. We're going to be talking about L squared and LZ. It's going to be a lot of fun. Let's dive into it. Okay, so we're going to begin talking about angular momentum. We'll start right here at the top step. I got some nice blue notes here, and I got this visualization of the entire ladder. This ladder for angular momentum with the top rung right up here. This is provided in the problem statement, the sample problem that we're doing, that L of Z all the way at the top is equal to L times H bar. And all the way at bottom, we have this L with a bar over the top, which we'll call L bar, times H bar. Now, those are given, those are postulates, but we can prove them, and we can prove the eigenvalues that we'll find, or the eigenfunctions that will wind up being lambda. I'm getting ahead of myself, but we have to start somewhere. We know that L squared, that being the total angular momentum, times some function of the top rung is equal to this lovely equality, where we have the angular momentum down ladder operator times the up ladder operator plus that z component of angular momentum squared plus h bar times that z component, all times this function. So we can expand this, or maybe I should say expand to then simplify. We can take out an L down over here, also while distributing this f top into each of our terms. So we take that out, we're left with this. Again, we're distributing that in. This LZ component times an LZ component, f top, plus h bar, LZ component, f top. Now, if you see what we did, we know that all of these two, are the same. We have LZ and f top. And then this strange little guy over here, which this is odd. Since we're at the top already, we cannot go any higher. So if we tried to do a ladder operator on this, we are at the highest point of any function at the top of this angular momentum ladder. So this becomes zero. This entire term right here will wind up going to zero, which actually makes things nicer. Things are a bit simpler. Over here, however, we know from up here, this being a postulate, we can plug in for L of Z. So we have LH bar, another LH bar, again, times this top function, plus an H bar, and once again, we have another LH bar times this top function from that LZ. So after this, what can we do? We can start to take some things out. We can start to make some things easier on the eyes. One of those things being combining our h bars, so we're left with h bar squared from these two h bars, and I'll take one L out. I'll leave one L in there, and you'll see where I'm going in just a second, because I'll also take these two h bars, and I'll say, hey, we have an L, so now we have this like term here, this h bar squared L times an f top, and that's lovely, because you know what we can do? We can take out this h bar squared. We can say, hey, this will be distributed around the whole thing. So what we're left with is this L plus 1, and then we'll also take out that f top. So this is a nice form. This eventually is what our L squared of f top equals. But what we can do at this point is say, hey, this is an eigenfunction. So our eigenvalue lambda is equal to this bit right here. H bar squared L times L plus 1, or if you want in a much cleaner way, maximum, so this is our lambda max, because again we're at the top of the rung, is equal to H bar squared L times L plus 1. So that's a lovely result that I'll box off there, and for neatness sake, I'll write up here in this beautiful blue color and rearrange just ever so slightly. And this is for our LZ equals LH. Again, at the top of the thing. Now, since that was simple, too simple I might add, we should get more complicated, or we should just do similar mathematics. So let's do the bottom step. Again, we'll start off with this L squared F bottom, which eventually I'll start abbreviating as BOT. So if you see that down the road and I didn't specify that, that's what it is. But I guess I did just specify that, so whoop-de-doo. Okay, the mathematics here are pretty much the same, except the order here of our ladder operators. We'll be starting here with an L plus, L minus, L up, L down, then an LZ squared for total squared, and here it's a minus H bar, LZ component, all times our lovely bottom function. So I've done a bit of movie magic in the time that we've last seen me, but that's okay, because the mathematics here are extremely similar to up here at the top step. Right here at the bottom step, though, it's very important to note, the order is different. So our ladder operator order is different. Here we have L plus, L minus, before we had L minus, L plus. And the concepts are the same, except for here, instead of being at the highest rung, so we were at the top here, and we wanted a ladder operator that said, hey, go one rung higher. We get all the way up top, and then we fall off that ladder, so our term goes to 0. Right here, though, we're at our lowest, and this ladder operator says, hey, go one rung lower. I'm like, I can't, man, it's the ground. So we go to 0. Same concept here when we plug in for L bar, H bar, our LZ component, which comes from here. I also wrote that there, and there, that we're taking as postulate. And yeah, algebra is pretty much consistent. It's the same, and then we're left with a new lambda. Again, that's our lambda minimum, which is written up here nicely in some blue, and that being lambda minimum is equal to L bar times L bar minus 1, so that's our key difference, times H bar squared for this bottom rung, that L bar, H bar, when L is Z. Okay, and that's it. So we know a bit more about angular momentum now. We know about ladder operators, how they act, especially this all-important L squared value, which I've included here. If we want to know for any point on this ladder what we can do, L squared times some function with quantum numbers m and L times H bar squared L times L plus 1 times that function again. We can use that, and again here, H bar m times that function for the Z component. Here, our m was equal to L, and our L bar here was at the bottom. Yeah, so that's it. Thank you.